This video is a continuation of the exceptions notebook, and we'll discuss the handling of exceptions. In the previous section, we saw an example of stack trace, which can actually help us to decipher how and where an error occurred. But how do we detect and handle exceptions at runtime? So the try statement allows us to do exactly that. The try statement consists of the try keyword followed by a colon. Then in the block that follows, we include only the code that may raise an exception. And we want this block to be as small as possible to allow us to handle only a few specific errors that could occur in that block. So following the try clause, we may have 0 or more except clauses that each handle a specific error or a specific set of errors. So in this example, we have a while loop that loops indefinitely. And inside the loop, we're going to try to get input from the user using the input function. And then we're going to convert that input to an integer. Now, if the user gives us something that's not convertible to an integer, then a value error exception will be raised. Without the try statement, this would result in an error halting execution, as we saw in the example above. But with the try statement and its except clause, which specifically handles the value error, execution does not halt. Instead, the except clause for the value error would be executed. So again, if the user inputs something other than a number, this function will fail and cause an exception. Specifically, this exception. When that occurs, the interpreter stops execution at this line, looks locally for an except clause that handles the exception, which it finds here, and then evaluates the body of that except clause. So here it's just going to print, oops, that was no valid number, please try again. The while loop will be allowed to continue again, and we'll ask the user for more input. So if we run this, we see that it asks us for a number, and I'll enter the letter Y and hit enter. You say, oops, this is not a number. Please try again. So now I can enter something like 42, which is convertible to an integer, and the code block exits without error. Now, I will point out that if an error other than a value error occurs within this try block, there would not be an except clause to handle it, and this would cause the interpreter to halt execution and issue the traceback that we saw in previous examples. Now, I mentioned that you can have one or more except clauses to handle the various errors that may occur, but you can also include multiple errors in the same clause by providing them as a tuple, as in the text here. You see that we have a runtime error, type error, and name error all in the same except clause. And so while this block would do nothing since it passes, you could handle all three of these types of errors with the same block of code. Or alternatively, you could break these up into separate except clauses if, for instance, the code required to handle each of them needed to be different. Now, if you want to have an except clause that catches any unmatched exception, then you can include an empty except clause. So let's consider the following example. The code within this try clause attempts to open a file, which may or may not exist. It then attempts to read a line from that file, and then convert that line to an integer after having removed the white space from the ends. So to handle the myriad of errors that could occur in this block, there are three except clauses here. The first is an OS error, which is raised if my file here does not exist. The second is a value error, which we've already seen is raised when the int function is unable to convert the string passed to it. And the last except clause is empty, meaning that this is a catch-all that will grab any exception raised that was not explicitly handled by a previous except clause. So there are a few things I want to point out. One, in the OS error except clause, we included as error at the end of the line. This is declaring the name error, ERR, and binding it to the OS error object that was created when the error was raised. Using this object, we can get more information about the error that was raised. In this example, you can see we're simply printing it out. So at this moment, the file myfile.txt does not exist. So if I run this block, you see that we did get the OS error, just as I described. And this error object here, when it printed, gives us this information saying that it was an error number 2, meaning there is no such file or directory, and then it gives us the name of the file. Now, the second thing I want to point out is that in the empty except clause, we used sys.exe_info. To use this, you'll also notice that we need to import the sys module here, but this function returns a tuple containing information about the current exception being handled. And so we simply print out the type here, which happens to be the first element returned to the tuple, hence the bracket 0 at the end.
But this gives you yet another way to get access to the current exception without using the as keyword. The third thing I'm going to point out is that also in this empty except clause, we use the raise keyword here, which re-raises the current error. This has the effect of passing the error up to higher levels of the code, meaning up the stack to whatever functions that may have been called to get us to this point in the code. Now, there are two more clauses that can be helpful when dealing with errors. The first is the else clause, which, if present, must come after the last except clause in your try statement. The else clause is executed only if the try clause did not raise an exception. So if we consider this example here, the try clause attempts to open a file, and if that file is open, meaning no exception is thrown, then the else clause will execute, where here it simply prints out the number of lines in the file and then closes the file. If the file didn't exist, then an OS error would be raised in the try block. And instead, the except clause would be evaluated and the else clause would not. Another point to make here actually is that in the previous example, we saw the try clause included several statements that could each raise an exception. Now, in practice, you may wish to break that up to limit how many things can go wrong in the block, one, and two, to help simplify the except clauses. Using the else clause, as in this example, can also help with this too. Now, in this example, we performed a very simple operation of the data of the file, and then we closed it all within the else clause. But what if the work to be performed on the file here could raise an exception? Now, with shared resources like files, it's always a good idea to ensure that they are properly closed or released, even if there are errors. And the finally clause can help us to do that. The finally clause is intended for cleanup operations that must be executed no matter what. This clause is executed as the last task before the try statement completes. So in the example here, we can see that our try clause simply raises an exception. Now, since there's no handling for the exception locally, the finally clause is going to be executed and it's just going to print goodbye. And then the exception is going to be re-raised to be handled at a higher level. So if I run this block, we'll see our statement goodbye followed by a traceback. Notice that we didn't have to explicitly re-raise the exception in the finally block. This is automatically done for us. So this can be a little bit tricky if this is the first time you're seeing it. So the text here at the beginning gives you the order of execution for a few scenarios. One situation here that's particularly interesting involves return statements. If we have a return statement within a try clause, and then another within a finally clause, the return in the finally clause will actually supersede the return in the try clause. So if I run this block, you see that we get false from the return in the finally clause instead of true from the try clause. So once again, we called finally return. This function went to evaluate the try clause, which simply returns true. Now, before returning true, at the end of the try clause, the finally clause is going to be executed, which also returns a value, in this case false. This, like I said, supersedes this return. And so you see in the output that we actually get false and not true here. Now, if we look at the divide function next, this function is going to perform a division of its arguments. And if successful, it's just going to print the result. If there's a division by 0, then an exception will be raised. Then the except clause handling the 0 division error will print division by 0. And then the finally clause will print the statement saying executing finally clause, just to let us know when the finally clause actually is executed. So if we run this block, we try to divide 2 by 1, which succeeds, and we see that it prints the result is 2.0. And then we see executing finally clause. If we do this again, but this time divide by 0, you see that we get the division by 0 statement printed, again followed by executing finally clause. And last, if we were to pass non-numeric inputs to the function, there is no except clause to handle this error, and the finally clause is evaluated before re-raising the exception. So in the output, we see executing finally clause followed by the traceback for the unhandled exception. Some exceptions may be given a value or an argument when they're created. This argument can be used to provide additional information about the error that has occurred, meaning that if you explicitly raise an exception, you can specify some additional data to be included with that exception object. And these arguments, this data, can be accessed from within the except clause to aid in cleanup or simply output to aid with debugging. To access these arguments, we need a handle or a name for the exception. We can either use sys.exeinfo, as we saw earlier, and find the argument at index 1, or we can use the as keyword to name our exception just as we did here. In this case, we bind the exception that is to be handled by this except clause to the name inst, inst. With that, we can access the arguments using the args attribute of the exception object. So in this example, the first line here prints out the type of the exception using the type function. And if you look at the output, you see that's printed here. The next line again prints out the arguments explicitly using the args attribute. Notice that the following line in the output is actually the same, yet the print here did not specify the args attribute. And that's because when the print function is passed an object to print, it attempts to call that object's string function, which is here in the comments, which should return the string representation of that object. And in that case, we see that the string representation simply includes the tuple of arguments, but that's not always guaranteed to be the case. The last 3 lines here again use the args attribute, but we're going to unpack the tuple into variables x and y, allowing us to print them separately on the last 2 lines. So hopefully this example shows you how you can pass arguments to an exception that you explicitly raise, and how you can get access to those arguments in an except clause should you need them.